Hello, this is the first in a series of videos which are designed to have a look at the basics of probability. And in this video, we're going to start with looking at some fundamental concepts. So as you can see here, I've got that probability is the calculation of chance. So we go from that sort of vague concept of what's the chance of this or what's the chance of that, or some sort of language of you've got a really good chance of something, to actually doing some calculations. And then we can call it probability as opposed to just an investigation of chance. So as you would be aware by now, there are two kinds of probability. One is experimental and the other one is theoretical. And I've got some descriptions of both of those there. And I guess in terms of mathematics, both are valid approaches towards probability, but it depends on what you're trying to get out of it, I suppose. So some probabilities can't be calculated theoretically because we don't know enough about them. So running an experiment is the only way to go. Other probabilities are best done from a theoretical perspective because the experiment might be too difficult to run. But they both have their own difficulties. So, for example, experimental depends on the conditions being just right and that you have enough time to run enough experiments to make it valid. Whereas in theoretical probability, what you need to get right is the assumptions, I suppose, into what you're doing, and additionally to that, you need to make sure that you are able to come up with the right numbers for the theoretical calculations to work. So a couple of key words here is outcome, which is the result of an action from the event, and the event itself, which is as it says there, the description of one or more outcomes as a result of an action. So typically what we're doing in probability is that we're trying to work out if it's experimental, as I've written there, it's the number of successful trials over the number of trials. And by success, it's basically what we're looking for. So it would be a bit weird, but if you were sort of like saying, what's the probability of failing a test, then your success is that that the person failed the test, even though it's not a moral success, but it's nevertheless an identified outcome we're looking for. In theoretical, we've got this kind of thing called matching outcomes or desirable outcomes or desired outcomes. So what you're really looking for is which outcomes match what you're looking for. That's what the top number is. And then the number of all outcomes is what we also call the sample space size. Speaking of which, yep. So here we go. Here's a little bit on sample spaces. So sample spaces, as it says here, is when you describe or list, I suppose, all possible outcomes for a particular event, I suppose. So the classic example of rolling a six-sided die here is that you've got 1, 2, 3, 4, 5, 6, or flipping a coin is HT. So typically we use the curly brackets or braces, and then we list them like so. And I've got a couple of examples here I won't go through. You can pause the videos for yourself and you can have a look at exactly how I've worked that out. Okay, here's complementary example here, event, which I wanted to go through very quickly. So the idea of a complement, I guess there are not two definitions really, but there's complement with an I, which means to pay someone a compliment, to say, oh, well done. And then there's complement, which means that one goes with the other. So like complementary clothes, maybe two sets of clothing that goes together. I don't know, it makes sense to me. So in complementary events, it's basically you've got one set of events or one set of possibilities, and then you've got another set of possibilities. If they're complementary, they go together, and if they go together, they form all possibilities. So my example here is like, what's the probability? Let's say rolling a die again. You've got one event which would be that the die is not prime, and then that would be the complement of that the die roll was prime. It's either not prime or it is prime. There's nothing else it could be. So between the two of them, it covers all events or all possible outcomes, and therefore they're complementary to each other. And do note that if one is complementary to the other, then the other is complementary to the first, if that kind of makes sense. So yeah, they're sort of reciprocal in their complementariness. I've got a note on notation here. So if we call A the event, then A dash like that, which is what I tend to use, or you might see A bar, A with the bar on top. That's the notation for the complement event. Okay, so if A is the complement of B, then A dash equals B and B dash equals A. Okay, so and this is just a very simple bit of arithmetic here. I'll just hide that little note there. Simple bit of arithmetic here is that since they do cover all outcomes, then the probability of A added to the probability of A complement must equal 1, right? It kind of makes sense, I hope. Or to put it another way, the probability of an event happening must be equal to 1 minus the probability of its complement. I hope that makes sense. It's common sense sort of stuff, but this is a really common probability calculation to use, and I've got an example in a subsequent video to show you that. So here's a notation that I wanted to go through with you. This one here, P or PR of A, depending on how I feel, I might have to say P or PR for probability of an event A, like so. Then we've got these two notations here that I wanted to go through. I might just even zoom up so you can sort of see that. The time banks, I think it's kind of pretty important. If you see A and then this sort of U shape B, close bracket, we say A union B, that's what I've got in blue there. So it's A union B. And when you see the union symbol, think of it like OR. So probability of A union B means the probability that event A or event B happens, and really importantly, or both. Okay, so as long as it matches one part or the other, then it's a match. So if I'm just trying to think off the top of my head, rolling a die, and if I said the probability that if A is the event that I roll an even number and B is the event that I roll a prime number, then A or B would be 2, because 2 is prime. It's even and it's prime, but it still fits within one of these. It happens to fit in both, but nevertheless it fits at least one. So 2 would be one of them, 4 would be even, 5 is prime, 6 is even. So all of those would be a match. So there you go. So, and 3 as well, I should have mentioned. I forgot that one. So anyway, so as long as it matches one of them. Normally you'd sort of see that combining two events like A or B increases the number of outcomes is probably the best way to think about it. The opposite, I suppose, is A intersect B. And intersect is like a joining word, I suppose. So we could consider it a match if it matched both A and B, as I've got here. So intersect means and it means because we're restricting effectively what's matching, we're going to get fewer outcomes. So using the same example I did before, then that would be even numbers, prime numbers. Then 2 is even and prime, so that would be in. 1 is neither prime nor even, so it wouldn't be in either of those. 3 is prime but not even, so it's not in. 4 is even but not prime, so it's not in. 5 is prime but it's not even, so it's not in. And 6 is even but not prime, so it's not in. So the only number that would match for A intersect B is 2. So you can see that's a big restriction on the set compared to what A union B was, where there's quite a few. So that's the difference between the two, and get used to this notation because it's used a lot in probability arithmetic, which we'll go through in a separate video, as well as describing what's happening in our sample spaces. So sneak peek ahead. In the next video, I might cover this first and then we'll do the specific ones in the next video. So very briefly to start off, to finish off with, sample spaces. Whenever we refer to sample spaces, we're talking about creating all those possible outcome or thinking about all those possible outcomes for a particular experiment or particular theoretical event. And the nitty-gritty of probability is either generating or counting the sample space. So sometimes it's easier to just generate the sample space so that we can manipulate it. Sometimes it's so big that we couldn't possibly generate it. But if we've got a systematic way of counting it, then we're good to go. Because remember, the basics of probability is down here, right? Number of matching outcomes over number of all outcomes. So if I can count all the outcomes or have a calculation that gives me the number of outcomes, it doesn't matter so much that I haven't listed them all, as long as I can be sure that the number I've got is right. And similarly for the matching outcomes. So that's the other key thing with sample spaces, I suppose, is if you can't generate it, if you can at least count it, that's good, or have a calculation that does the count for you. That'd be good. Here I've just listed the fundamental ways that a sample space is generated by a list, by a table, by a tree, by a Venn diagram, by a Carnot map, or a two-way table sometimes they're called. So they're common methods, and in the subsequent videos I'll have a look at some of the more tricky ones, trees, Venn diagrams, and Carnot maps. And I'll just finish by talking about the two pretty straightforward ones. So when you've got a small number of outcomes, like flipping two coins, it's probably easy just to list them. And technically, you should use braces and then put the different combinations, I suppose, down here. And as I said here, you have to be systematic. So somewhere, so for example, flipping two coins might start with two heads, and then I might say, okay, I'll make the second one a tail, and then I'll make the first one a tail, so head, tail, tail, head, and then I'll make both of them tails. And that's a systematic way of listing them all. As soon as it gets more complicated, though, just drawing a list has the problem, even though it's nice and simple, has the problem of, do you get every single possible outcome? Tables is a step up in that regard, because it usually forces you to generate every single outcome simply by matching them up. As I said here, it's good when you have two parts to your event. For example, rolling two dice. And I've got an example. Oh yeah, they're sometimes called lattice diagrams. And I've got an example of a table here. So I'll just zoom up again so that you can just focus on that particular part. You can see here that if this is rolling two dice, I've got 1, 2, 3, 4, 5, 6 here, and 1, 2, 3, 4, 5, 6 here. But I don't make this 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Really, this section in here is to describe what outcome you are looking for. So, for example, if you're looking for the sum of the dice rolls, then that might say 2, that will say 3, that will say 4. This one down the bottom here will say 12. Or if it was the product multiplying, that'd be 36, and this would be 5, and this would be 9, etc. In this instance, I've just got Y's and N's. Y's for yes and N's for no. Pause the video and see if you can figure out exactly what my matching outcome was in this instance. I deliberately chose one that was a little bit not straightforward for you to see. So I wonder if you got it or not. But this is what it is. Basically, if the number down here is a factor of the number up here, then I'm calling that a match. So you can imagine this might have been a red die and this might have been a blue die. And if the red die ended up being a factor of the blue die, then we called that a match. So does 1 go into 1? Yes. Goes into 2, goes into 3, goes into 4, goes into 5, goes into 6. Does 2 go into 1? No, but it does go into 2, so that's a yes. It doesn't go into 3, but it does go into 4. It doesn't go into 5, but it does go into 6. 3 doesn't go into 1, 3 doesn't go into 2, 3 goes into 3, doesn't go into 4, doesn't go into 5, but does go into 6, and so on. And that was how the no's and yeses were listed. So you can get quite tricky sorts of outcomes listed here. It's not just a simple 1, 1, which actually tells you nothing at all. Usually you're looking for a more specific outcome than just what the two faces say. It's more likely you're adding, multiplying, or doing what I did just then. Okay, so looking ahead, and then I'll stop the video there. Next, we're going to have a look at weighted trees and do a quick example of that. And then I'm going to do a video on Venn diagrams. And subsequent to watching these videos, there is some textbook work that you can use to practice. And ultimately, with probability, I find the principles fairly straightforward, but the number of different scenarios that you can come across is where it becomes more tricky. So I would absolutely be encouraging you to get hold of the theory pretty quickly, and then practice and practice and practice as much as you can. And that'll be your key to success, being able to recognize problems and say, oh, I can solve it in this kind of way. Okay, I'll leave that video here, and I'll see you next time.